Michelson's interferometer. This is a Michelson interferometer. See, this light is shining on the mirror. This mirror is very weird. It half reflect and half transmit. So the one source split into two, okay, and these two go back and go back, recombine here, so they get interference, okay. And what you can see is from here, because this one and this one, they are the same, okay. So we can look at the interference. An interferometer is a device that can be used to measure length or changes in length with great accuracy by means of interference fringes. We describe the form originally devices and built by A. Michelson in 1881. And we see the two lines. What is their path difference? They move in the same medium. So this one go 2D2, this go 2D1, and it go flex to here. So their path difference is 2D2 minus 2D1. Okay? Now we see the phase difference when you look at here is 2D2 minus 2D1. Okay. If this movable mirror, which attached to the body we measured, move half lambda, then the path difference changes to half lambda is lambda. And the observer will see the fringe pattern shift by one fringe. Okay? By such a technique, the length of the object can be expressed in terms of the wavelength of the light. Okay? That's a wonderful thing. Okay? A wonderful thing. So, in 1907, he got Nobel Prize in physics.
We will now use this setup to view white light interference from a Michelson interferometer. White light from this bright quartz halogen point source is collimated by this condenser lens and directed through a heat filter into the Michelson interferometer. The interference fringe pattern can be observed with the use of a lens at the exit of the interferometer on the screen. When the two paths of the interferometer are of very nearly equal length, light from the two paths will interfere destructively at one or more wavelengths. This creates fringes of non-spectral colors, that is, fringes of white light from which one or more wavelengths have been removed. The length of this path can be varied by adjusting the position of this moving mirror using this micrometer. This mirror, called the fixed mirror, can be rotated using two screws on the back of the mirror. When the two mirrors are aligned perpendicular to their optic axes, circular fringes can be obtained. We now start with the moving mirror in too close to obtain fringes and slowly move it outward so that we can see the sequence of colors produced. Now the mirror is out too far to obtain fringes. The moving mirror has now been returned to the equal path length position, and the fixed mirror has been tilted so that we can see line fringes. Once again, the mirrors have been aligned perpendicular to their respective optic axes, and a hot match tip is inserted into one path of the interferometer.
This device consists of a microwave emitter, a microwave receiver, and a bar graph display whose length is proportional to the intensity of the microwaves picked up by the receiver. The microwave beam first strikes a mesh screen, which reflects about half the beam and transmits the other half. Each of these beams strikes a metal sheet and reflects back. Part of each beam reaches the receiver, where they combine. The two beams interfere either constructively or destructively depending on the phase difference between them, which depends on the path lengths followed by each of the beams. If we move one of the mirrors to change the path length of one of the beams, the intensity at the receiver shows a regularly spaced pattern of highs and lows.